I should say. Let's look at something though. I want to look at a derivative rule, and there's an apparent hole in our derivative rule. Remember, we said we've been able to do stuff like this for a while now. We could say, like, for example, if y equals x to the fifth plus 3. You guys know how to use the power rule and find dy dx. And we now even know how to do stuff like this. If f of x equals something like, well, hang on. And then the associated integral rule that goes with that, we know too, the antiderivative rule. What I want to look at is the trend. If we look at this for different powers of x, right, we know something like this too we could do. You know, we know how to differentiate that using u substitute, or using chain rule, right? And then if we move over to the antiderivative or integral side of things, we know the corresponding, we could do something like this if we wanted to, right? Using our associated power rule for integrals. And now we could even, let's just take a little bit of practice with this, we could even do something like this. Even do nasty stuff like that. That last one there, how would we approach that one? Okay, use substitute. Now we can't break this one in two because we got this power up here, but I heard use of, say it again. Go ahead, go ahead.
I think you need to do integral of x and integral of x squared plus 3.
Okay, but, okay, now, you have to be a little careful with that. We can't, we're okay differentiating and integrating term by term. So for example, and then this is a really good maybe topic for just a very brief review. We can do stuff, we can do stuff like this. Yeah, pen, not eraser. We can do stuff like this, where if we have y equals 3x squared plus sine x plus square root of x, we can differentiate that by just breaking it up into 3 separate small derivatives, right? Differentiating term by term. And if we have stuff like, say we want to integrate something maybe even similar to that. 3x squared plus sine x plus, we could even take care of something like that term by term. But the key reason that we can is that these are terms and not factors. They're being added. Or they could be subtracted too, right? But here we got a little problem. Here, because these are being multiplied, I don't have that luxury. Okay? So what's my strategy for this guy then? This is the one that up until like a week and a half ago we would have been at a loss. Yeah, we got to see if we can make a variable substitution, a u substitution that's going to make this easier to deal with, right? And if we get real theoretical about this, and we kind of really try to evaluate, you know, what's causing the problem here? Why is this such a difficult? Yeah, because we've got this quantity to the 5 halves. That's really the part that's causing problems for us. Now, if that 5 halves weren't there, right? If this power were being, if we're taking the power of a sum, we could just distribute the x and use the power rule, right? That would have been easy. It's the fact that we've got this quantity, this x squared plus 3 to the 5 halves that's causing the problems, right? So that's where we got to make our u substitution. We've got to say something like u equals x squared plus 3, so du becomes 2x
Plus c.
no, 2x, what am I forgetting?
Oh, dx.
dx, there you go. And so it looks like we've got an x dx up here, right? And then we've got a u squared plus 3 to the 5 halves. So if I make my substitution, what do I end up with? If I go from here, what is that then in terms of u's? So I've got a to the 5/2. Now that's better, isn't it? Now, we've still got that 5/2 power in there, but now I've just got a variable to the 5/2 instead of a polynomial to the 5/2. Much better, right? So, u to the 5/2, and then I've got an x dx, which is equal to divide by 2. Okay, there's my x dx, so I got to divide both sides by 2, so I get a 1/2 du. And now that's easy, right? Now that's just a power rule problem. Should we finish it? Okay, why not? Let's finish it. Okay, so then if we finish this up, what's that equal to? What's my power rule for integrals tell me about that? Oh, good, there we go. Okay. Good, so we're gonna divide by 7/2, which is the same as multiplying by 2/7. So we've got our 1/2 times 2/7. So the 2's cancel. And I gotta put my plus c out there, right? And so it looks like 1/7 u to the 7/2 plus c. Last step then would just be, yeah, okay, we'll just reverse that substitution and substitute back, or go back to x's. So the u's are x squareds plus 3's. So this just looks like 1/7 times the quantity x squared plus 3 to the 7/2 plus c, right? Okay, good. And you guys will continue to get some practice with that stuff, and it's working great. But let's look at this power rule a little more closely. If we do the integral of u to the 3 du, that's just u to the 4th over 4 plus c, right? Integral of u squared du is integral of u to the 1 du is okay. And we could even go down and let's how about if we get u to the 0, what's that going to be? Fine. That actually works though, doesn't it? That's just u to the 0 du is the same thing as du. And what do we get for that? What's the antiderivative of du? U. And that, honestly, even though it's not convenient to do, it makes no sense to apply the power rule there, it's overkill, it actually works, doesn't it? I mean, it really does work. We wouldn't write it that way, but it's consistent at least, isn't it? Okay, let's keep going. So we got u to the minus 1, u to the minus 2, u to the minus 3. Let's skip down here to u to the minus 2 real quick. What's that one going to give us? Okay, u to the minus 1 over minus 1, which we'll just say times minus 1. This would just give us u to the minus 2 over minus 2 plus c. But what about this guy? What about this lonely soul right here? What does the power rule predict for that? U to the 0 over 0. Whoa, red lights, red flags, sirens. We can't do that, right? U to the 0 over 0. Okay. That is a fail. It didn't work. Power rule broke down there. Okay, so there is a hole in the power rule. Now it'll work for any other power. It would work for u to the minus 0.9999999. It would work for u to the minus 1.000001, but it doesn't work for u to the minus 1. We got a problem with that. Okay, but sometimes problems are just opportunities for some new learning, right? Okay, so what we have to do here is we have to look at a different function that's gonna bail us out here, okay? The natural logarithmic function. So I forgot my notes, but that's all right, we'll make do. So let's see. Okay, so now, first of all, let me preemptively correct you so you don't sound like a doofus when you talk about this in college, because there's a real tendency for people when they first start working with this. What's that?
I'm gonna have to sound like
No, you're not. It's like a script ln is what we use to say the natural log, and I think it goes back to French. It's like logarithm naturel or something along those lines. Forgive my horrible accent. Anybody that's in French, you can laugh at me. But what you don't want to do is you don't want to call this the ln of x, because mathematicians, if you say that in college, they'll just be chuckling at you. You don't want to do that. It's when you see that ln, you call it's the natural log of x. Now you can. It's okay if you just call it a log. If you're, I mean, math is so confusing this way in a way. Say it again. Natural log. It's the natural log as compared to, or as distinctly different from, say, the base 10 log, which we call the common log. But this is the one that we use the most, by far, is the natural log. And so, if it's really clear that we're just using natural logs, sometimes people will just say the log, and it's understood that they're really just being lazy and they mean the natural log. But really, what you should call this is the natural log of x, okay? Not the ln of x or ln of x, it's the natural log of x. Now, the natural log, yes, sir?
Why do they abbreviate LN?
Because I think it's French. I think it's logarithm natural or something along, I can't remember exactly. But that's why they call it ln. And they give it its own special notation and name, because really, as we're going to learn, we're going to look at logs here a little bit. We can do any base of log we want to. We could do a base 10 log, which is real common for us because we have a base 10 number system. We could have a base 7 log. We can have any base we want to. And as we explore these, logs are really, I'm not just talking about like being in the mountains. Logs just in general are really, and mathematically, are really interesting here. I'm not trying to advocate for the timber industry or anything. Logs do some really interesting things for us because they predict a lot of the growth that happens in nature adheres to exponential and logarithmic functional behavior. It's like, for just as a quick example, when people have a really just poor innate ability to think in terms of exponential growth. People do a great job of thinking linearly, but it's an interesting mathematical study. Kids, actually, very young kids, are better at, just intrinsically, before they start being polluted by math teachers, I guess, they're better at sort of just conceptualizing exponential growth than adults often are. Because part of it is we don't have to deal with it. Rarely do we ever talk about exponential growth, but it's all around us. Like you could say, for example, tell me if this doesn't sound like an innocuous statement, maybe even a positive statement. If I said something like, yeah, we're really pushing, the Pendleton's a little bit depressed economically, we're really pushing for some growth. It sounds great, and maybe that is good. We're just gonna push for some, sort of aggressive but not ridiculous growth. We want to go, let's say, 12% annual growth. 12%. That seems reasonable, doesn't it? Okay, but whenever you start to hear, and I'll defend this statement here over the next, few days and weeks. Whenever you hear somebody talk about growth, about percent growth, what you always want to do is you don't want to think about it in terms of the growth rate, the percent, because that doesn't sound very impressive. What you want to do is you want to think about it in terms of the doubling time. And you can always use what's called the rule of 72. If you divide 72 by the annual percent growth rate, it tells you the doubling time. Now that gets to be much more telling. If we were truly gonna have sustained 12% growth in Pendleton, let's just think about what that would look like over the course of a couple generations. 12%, well, 72 divided by 12 is what? 6. That's telling you that the doubling time for the population would be 6 years. So let's just say that, let's just assume that that had started when you were in kindergarten. Okay? So then every 6 years, what's Pendleton's population? 18,000 ish. I think it's
16.
I think it's about 18. I'm pretty sure it's about 18. I know it's more than 7.
A lot of people migrate.
So let's say, let's just say hypothetically, say it's 18. So by the time you're in 6th grade, that would go from 18 to 36. Well, that's pretty big, okay? That's pretty big. But by the time you go from 6th grade to graduating from high school, all of a sudden you're at 72. So you go away to college, maybe you study abroad for a year, you come back 6 years later, you're at 144,000 people. Okay, you get married, you're having a family, you decide to move back to good old Pendleton. It's a great place to raise kids. So you come back 6 years later when you're, I don't know, what are you going to be then, like 24 or something, and so young. And all of a sudden now it's up to 288,000. Man, by the time you retire, this place is going to be as big as Portland. You think that a community can grow that fast? And no, you can't. The infrastructure can't keep up. You can't put in the sewer systems and the roads and keep the such fantastic schools growing at that rate. You can't. You can't do that, right? And so that's why it's so crucial to always really honestly that's from now on always do that. Apply the rule of 72 because the doubling time is what really gives you an idea of is this guy is this realistic? Even people talk about economic growth. People get so upset when economic growth is only 2% they want to have or less. They're pushing for 4%. That's not sustainable. There's no way. The rule of if we were going to have continued 4% economic growth as a nation, think what that would mean. That would mean that every 18 years you're going to double the size of the U.S. economy. That's not going to happen. In index dollars, there's no way that's going to happen. That's just not, and that's probably not a healthy thing to have happen. So, it's just, you can kind of see here, though, that we're entering a realm where this is a little more counterintuitive, but it's, as much as it's counterintuitive, it's actually also more descriptive of what really happens. Okay, so let's, back on track here. I digress. It's nice. It is nice digression. I agree. Those are interesting topics. Okay, so what is the natural log function? What does it look like? Well, let's do this in 2 ways. First of all, let's just look at a graph of the natural log function, and then we'll look at how the function is actually developed. So if we were to just graph the natural log, and you all know this, I'm sure. You may be a little rusty, but I know that you've talked about this. And I'm pre-calc, you would have done an awful lot of this, I'm assuming. Who can remember if I graph the natural log function, what it looks like? Think now. Think back. Think back. It would have been back in pre-calculus, yeah. You would have done an awful lot with this. And you would have done some of this. You would have been first introduced in some detail to this probably in Algebra 2 honors. Yeah, okay, it goes, yeah, you're right. It's going to go, I think you might have had that upside down, but you have the right idea. It's doing this. It's going like that. Remember that? A log function is the one that starts aggressive and then peters out real fast, right? Okay, it goes through the point 0, 1. Or excuse me, 1, 0. Okay, and that's, I kind of squared that off a little bit too much, but you get the idea. Log functions, log functions grow very, very slowly, right? And that's one of their interesting and important properties is that they grow so slowly. At least out here they do. Down here they grow very rapidly. Okay. Now, that's what it looks like. How do we define it? Well, the natural log function, it turns out, is defined like this. This is going to look interesting. It's going to look like something you've seen before. It's equal to an area function. It's the area under the function y equals 1 over x. But we're going to call it t, so it's going to be a dummy variable. You'll see why here in a second. From 1 up to x. Okay? So this looks like that the functions that we drew and the areas we talked about when we were talking about the second fundamental theorem of calculus. Remember, with this stuff we had if I look at the curve 1 over t, it looks like that, right? And if that's x equals 1, or t equals 1, and say this is t equals x, then this area here is what defines, that's what defines the natural log of x, right? The numerical value of the natural log of x is just the area under an inverse function starting at 1 and ending at x. Okay. Now you can kind of see, can you take that picture of an area under a curve and can you sync that with that picture? Okay, this is an actual graph of the log function, right? So for example, the log of 1 should be 0. Let's just make sure that makes sense. Well, that does make sense, doesn't it? Because if I'm adding up the area under the green curve from 1 to 1, it's got no width, and so it's the area would be 0, right? What's the log of, oops, wrong way. What's the log of, say, 2 going to be? Well, the log of 2 is that number right there. The log of 3 is that number right there, but you can see that as I move up here, the values of y are starting to increase pretty slowly because the area under the curve is starting to accrue more slowly because the curve is getting so low, right? As this curve drops down and it gets closer to the t-axis, as I inch this x out, I'm really only adding really small pieces of area, right? Makes sense? Okay, now does it make sense that oh gosh, let's just sit there and just laugh at my ineptitude. What if we take a value like negative, or like 0.5? If x equals 0.5, that's going to give us a pretty large negative answer, right? When I evaluate the log function at 0.5. Does that make sense?
Yeah, because it takes so long.
Okay, now why is it negative? If I go back to like 0.5, if that's my x value, how come that's giving me,
To the left is 1.
okay, because I'm adding up the area backwards now, right? If I add up the area from 1 to 0.5, I'm going from right to left. Remember, that's one of the quirky things we said about area, is that it's considered to be positive when we add it up and we reckon it from left to right, but negative when we add it backwards, right? Okay, and you can see that it really picks up steam. As I go back to like 0.1, well now, this curve is starting to get a lot steeper, and so I'm actually adding a lot of area with each little minuscule bump to the left, right? And so it's getting much, much more negative relatively quickly. Okay, I got it right this time. And so you can see that that's starting to plunge down pretty rapidly. Okay, get the idea? Okay. All right, so whoops. Okay, so we are going to come back to this, but that's two pictures to hang on to mentally. We'll come back and we'll really analyze those things and dissect them mathematically. But let's just for now, let's just take a look at some properties of logs. Well, for one thing, oh, well, you tell me, what's the domain gonna be? I guess we should probably tackle that real quick. If this is our natural log function, what's the domain?
13 average. 0, infinity, or negative.
Jeez. This pen is, it's kind of starting to weigh out on me. It's better to run out. Yeah, what's the domain? So, looks like all values, could X ever equal 0? Doesn't look like it, does it? And it can't, because if we look at the way this is defined, a 1 over t graph, it's asymptotic on the y-axis, isn't it? And so what do you suppose is going to happen to that area as I get infinitely close to, from the right, to x equals 0? Yes, it's going to get infinite, isn't it? Eventually, it blows up to the point where there's, it's without limit. And so that explains why we can't ever actually get there, right? So wouldn't it look like this? Is there any upper limit on x?
Negative.
I mean, it grows without limit, doesn't it? There's no reason I'd ever have to stop moving to the right. So the domain is just all positive numbers. Okay? What about the range?
Negative infinity.
Clearly it goes down to negative infinity. Is there some horizontal asymptote up here, or does it grow? Always. Yeah, it grows. It grows, and it's never halted by an asymptote. It grows slowly, increasing, just plods along, but it grows forever. And so the range is all reals. Okay, what can you tell me about anything interesting you can tell me about the first derivative of that function before we even start to begin to talk about the calculus of the function? Just based on the graph, what can you tell me about behavior of the first derivative of a log function, natural log function? Didn't that go? No, it never does, huh? And it's almost, I'll give you a hint, it's almost interesting in the fact that it's so uninteresting. We always said that no, never does. The exact value changes, but what's the sign of the first derivative always? Positive. It's always increasing, right? We'd say in math this is a monotonic increasing function. There's no turning point. And we spent all that time with optimization. We always look for the interesting parts, or the places where the derivative changes sign. The critical numbers. Well, there aren't going to be any here, are there? Right? This thing is always always uphill. We're in. What about concavity? Well, okay, and the sign of the concavity is always.
It's always going to get down.
It's always concave down. Yeah, so negative, right? Sad function. Sad, right? Concave down. Okay. Good. Okay. And it's continuous, right? Smooth function. Okay, go ahead. Okay, some properties of logs. There are some interesting properties of logs. Okay, we know that. Well, I don't know if this is so much property, but we know that the natural log of 1 is 0. That one's not such a big deal. But there's some other properties that work for all logs that are very interesting. The natural log of a product equals what? Do you remember? The natural log of the product of A and B.
Oh.
Yeah, we do. We do. Oh. Now, there's a way you can think about this and conceptualize the arithmetic properties of logs. What logs do, and we actually harness this power in calculus. There's a whole technique that we'll get to here in a little bit, where we can actually purposely take the log of both sides of a function to make the arithmetic easier. Because what logs do is they ratchet everything down one level of complexity. If you look at kind of the arithmetic ladder, if we kind of think order of operations stuff, we start at the very bottom with addition and subtraction, and then we've got multiplication and division, and then we've got exponentiation. Wouldn't you agree that those are getting harder as you climb that ladder?
Then put the next one in parentheses.
It would be parentheses, which kind of starts over again. But we'll just, these are the three that are really, well, it's only the first three rungs of the ladder that are really affected profoundly by the logs. But when you agree those get harder, adding, subtracting, that's pretty easy stuff. Multiplying, dividing, that's a little harder. Exponentiation, well, way harder, right? That really complicates things. Look what it does when we take logs. When we take logs, it moves these things down on the ladder by one. Okay, so for example, the natural log of a product becomes
Add addition.
a sum, the sum of the logs, right? You see that? So here's how we say that. And I think it's nice, it's like you can remember the lyrics to a song, because there's music that goes with it. If you hear it said, I think it's easier to remember. The log of a product equals the sum of the individual logs.
That is nice.
Okay, the log of a product equals the sum of the logs. Okay? The log of a product equals the sum of the logs. Right? Okay?
I like the latter thing better.
The latter thing better. But you see what that did? It pushed us from multiplication down to addition, right? Okay, now what do you suppose happens if we do a quotient? The natural log of a quotient equals
Natural log.
subtraction. Yeah, there you go. The difference of the logs.
So is it always the numerator before the pronoun?
Yes, yes it is, yeah. Okay, now what about a power? The natural log of a power. What do you suppose that equals?
In natural log.
Yeah, product. So we're gonna take that power, that exponent out front, and it becomes n times the natural log of a. So look what it is. So now we get exponent becomes product. See, it pushes everything down. And so we literally, like I say, this technique of logarithmic differentiation is a wonderful technique. It makes things so much easier. We'll take the log of both sides, do the calculus, and then undo the log of both sides using its inverse function, which is an exponential. Okay? But that's a little ways away, but that's a really powerful technique for us. Let's practice this a little bit. Let's practice simplifying some statements using these logs, these properties of logs. So how could I do something like this? Let's say, how could I say, how could I simplify that? These are properties of logs.
Natural 10 minus
Natural log 10 minus natural log 9. Make sense? It's quotient. Okay, how about think about that one a little bit.
1/2 natural log.
Ah, okay, good. Now, and you guys you're training, you're starting to do this just very naturally. When you see in calculus, when you see a radical, you're always thinking in terms of a rational exponent, aren't you? Right? Because our properties in calculus of integrals and derivatives, and even like properties of logs, they all revolve around that exponential relationship, or many of them do. So we'll write this as the natural log of the quantity 3x plus 2 to the 1/2, and now it's obvious. Now we have a log of a power, and so we can pull that exponent down front. Okay? 1/2 natural log 3x plus 2. Now, can we do anything with this? Because that's always the question. I can totally understand why that is the question. So it seems like logs should be able to simplify everything. But what happens when you get to the bottom of the ladder? Can you take it down the rung from there? No, you can't. You can't. You can go from powers to products. You can go from products or quotients to sums and differences, but you can't go any lower than that. So we're stuck with that. That's right. Okay, how about, okay, and this one seems really simple, but be careful with this.
You do a product.
Okay, good, because there really are three factors there, aren't there? 6 and x and 5, right? I've got 6 times x divided by 5. So that's really, and you can do this in 2 steps if you want to. We could call this the natural log of 6x minus, right, the natural log of 5. And now that's a product, so we can split it. But really, you don't even have, you probably could just skip that intermediate step and just go right down to natural log of 6 plus natural log of x minus natural log of 5. Right? Okay. Well, enough of this easy stuff. My gosh. I gotta challenge you. I gotta challenge you a little bit here. Now you can kind of get an appreciation for how valuable this is. Here's where logarithmic differentiation would be used maybe. Okay, now this, see if you can, I got paper here, but I wanna see if you can concentrate on this and write this one all the way out. Think about all the stuff that's going on. So everybody write this down. Walk me out.
Is that x cubed or x to the cube root?
That's a cube root. A lot going on with that one. There's lots of logarithmic action in there. What I'm actually going to do, I'm going to give you a short, I'll make it very short, but I'm going to give you a sort of a pre-calculus review little assignment, where you got to just go through and practice some of your algebra using logarithmic properties. We use that a lot in calculus, so I'll make it real short, but that'll be the first thing you're going to see here in chapter 5. Okay, we're about out of time. We can, I don't know if we'll get this written down or not, but so can we name all the stuff that's going on here that the logarithms are going to help us out with? What do we got?
X squared plus 3.
Okay, so we got so we got a power I can pull down front, right? Let me just mark this up a little bit. Maybe we'll do this tomorrow, but I can pull that out front. Now what about this quotient? Okay, everything on the bottom is going to get subtracted, isn't it? Right? And then I've also got, what about this guy? Okay, that 1/3 is going to come out in front of that log, isn't it? It's a power. So if I had to write that all out, it's going to look like 3 times the natural log x squared plus 3. We'll pick it up tomorrow. And then I'll let you work on this stuff.